Hi, I'm Bill Vales. Today I'm with Tom Vales, also known as Dr. Electricity. Tom is on the adjunct faculty at Suffolk University working in the physics and electronics department. For this segment of Fun with Science, we're going to explore some of the basic principles and characteristics of radioactivity. Welcome, Tom.
Well, thanks for having me.
Glad you're here. It seems like every show that I do with you, I start off somewhat speechless. You have an array of stuff here. So how would you like to start this conversation on what the audience needs to know about radioactivity?
Okay, Bill. I think we'll start with some pretty basic definitions. First, with the atom. The atom has a nucleus that is made up of protons and neutrons. The protons are positively charged, the neutrons are zero. And around it, the electrons are orbiting the nucleus. The number of electrons in an atom equals the number of protons because an atom is electrically neutral. Now, there's a couple numbers we're going to be using today that I'm going to give you some insight on because it'll help you to understand more what we're talking about. One is the atomic number, and the atomic number is just the number of protons in the nucleus of an atom. That's it. The other number is the atomic weight, and that is the combined weight of the neutrons and the protons. And the electrons are so small that their weight is negligible.
Okay.
But those two terms, atomic number, number of protons, atomic weight, combined weight of protons and neutrons.
Okay. It's somewhat amazing when you think about it that objects that small can be weighed. I mean, I understand that they have weight and mass, but it's amazing that they can weigh it. So the picture, at least I have, and not completely accurate, but you had the protons and neutrons in the center.
Right.
Okay. And then around it, orbiting around it, are electrons. Now that orbiting isn't quite accurate, but that's the picture we were given in high school, and that picture has been.
You could call it more an electron cloud.
Right.
So.
Okay. And that was developed, that model was developed by Niels Bohr?
Yeah, the Danish Grand Master. He was an incredibly smart man.
Nobel Prize winner?
Oh, yeah.
Okay.
One other term we're going to mention now and we will pick up later is isotope. And what is an isotope? If you take an element and you leave its atomic number alone, it has the same atomic number, but you change the atomic weight by adding or taking away neutrons, it is called an isotope. Okay. Isotopes are typically radioactive even if the parent atom was not.
Okay. So if we have a hydrogen isotope, here's hydrogen, yep, which has one proton,
yep,
okay, which is positively charged,
right,
with one electron in its electron field,
right,
negatively charged. Now, an isotope of hydrogen, put your fist next to mine. Okay, that would be an isotope.
Right.
Your fist is a neutron.
Yep.
Mine's a proton.
Yep.
There's still one electron.
Right.
And this isotope is called?
Deuterium.
Deuterium.
But it's not radioactive.
Okay.
So let's add another neutron to the mix.
Okay, so now we have one proton, that's me.
Two neutrons.
Tom's two neutrons, one electron. So now we have an atomic weight of three and some change.
Three, yeah.
Okay. Okay.
And it's called tritium.
Okay. So hydrogen, in the simplest, is really a simple example conceptually, to conceptualize, of a isotope. You have hydrogen, deuterium, and tritium.
And tritium is radioactive.
And tritium is radioactive. Okay.
We will mention that later.
Okay.
If you
No
compare,
quiz on this.
If you compare radioactive elements with the other elements in the periodic table, you'll see that the majority of elements are stable. They don't change. If you have a block of copper today, you're going to have a block of copper 10 years from now. They just don't change. Radioactive elements, on the other hand, are constantly changing. They are in a constant state of decay. And as a result of this decay, they emit particles.
Okay.
They emit three emissions, okay?
Okay. These are the radioactive
elements
elements.
only.
Okay.
Three types
All right.
of things they emit. The first one is the alpha particle. And the alpha particle is made up of 2 neutrons and 2 protons. And it's basically a helium nucleus.
Let's make a helium.
Yeah.
Okay, so there it is.
Yep.
2 protons.
2 neutrons.
2 neutrons. That's a helium nucleus.
Alpha particles have the least energy and they have the least amount of penetrating ability of any of the particles. Okay, that's not to say that they're not dangerous. Okay, they can be very dangerous. But as far as if you had a mineral in front of your hand that emitted alpha particles, your skin would stop it. You'd be in no danger. The only danger you could be in is if you swallowed something with an alpha emitter on it. Then it's in close proximity with your organs, and that's not good. The second one is called a beta particle. And a beta particle is nothing more than a high-speed electron that is emitted from the nucleus. And its penetrating range is probably, if I recall, about 6 centimeters into the human body. It has more energy than an alpha particle. It can do more damage.
Okay, so a centimeter, 2.54 centimeters per inch.
Yeah, so that would be about 12 centimeters.
Okay. Okay.
Then the third one, and this is the real nasty one. This you don't want to get near this one at all. It's not a particle, it's a ray. And it is a high-frequency, high-energy ray, akin to an X-ray. They're in that same thing, but even worse than an X-ray.
Yeah.
It's called a gamma ray.
Okay.
Gamma ray can go through every part of the body without stopping.
Okay.
Everything.
Okay.
And it can cause genetic mutation as a result of its travel through the body. So the gamma ray is the worst one out of the 3.
Okay. But even an X-ray could cause, if you used enough X-ray or too much X-ray, that could cause issues with mutation.
Some of the first people that experimented with X-rays, of course, it's kind of hard to make yourself aware of something that you can't see or you don't even know is there, suffered severe burns. And actually, X-rays properly used and radiation properly used can actually help cure cancer.
Yes.
But it's knowing how much and where to put it that makes a difference.
Yes. Yeah. So I mean, with all these particles and technology, it's important to understand that there's positives and there's negatives associated with how these things are used.
Yep. Oh, yes.
Particles are used.
Yeah, you can.
Okay.
So,
all right.
Just one more thing to say, and then we're going to do a little demo.
All right.
As far as these emissions that radioactive particles elements give off, they can give off 1, 2, or all 3.
Okay.
It depends on the particular makeup of the element. Okay, so some elements give off, say, a lot of alpha particles. They're called an alpha emitter. Same with like a beta emitter.
Okay.
Then others, as we will see, give off all of them.
Okay. Now, when you say elements, just for our audience, we're referring to elements that are naturally occurring. These are the elements in nature that that are naturally occurring.
Yes, that's true. Uranium, there are, oh God, hundreds, if not thousands of mines out in the Midwest, in Canada, and now in the Congo, where they're digging up a lot of this radioactive stuff. So yeah, it's been around us for, quite a while.
Quite a while, okay.
Okay, I'll just give you a couple of examples of an alpha emitter. Would be radium and uranium and americium. A beta emitter would be strontium-90.
Okay.
And a gamma emitter, cesium-137.
Okay.
All right, so we're going to do a little comparison testing over here to give you an idea of what's doing what.
Okay. I'm going to put on some gloves.
That's fine.
I just feel like I should put on gloves, not that
no, it probably
these flimsy gloves are going to...
Oh,
okay.
They'll stop alpha particles.
Okay.
No, we're not doing this one yet. Okay.
Now, Superman didn't have a problem with this stuff.
Except kryptonite.
Kryptonite.
All right, we have three things we're going to be using here. A piece of lead, more commonly referred to as lead flashing, for your around your chimney on your roof. A piece of pine board, just standard 3/4 inch pine board, and a 1/8 inch thick piece of aluminum. All right, so the first thing we're going to do is we're going to take the americium.
Now, what device is this?
Oh, we're going to use a Geiger counter for this. The workings of a Geiger counter will be discussed later, but for right now, this is a device that gives you the intensity of a radioactive source. And we'll turn it on here.
Okay, now, there's nothing, well, there's actually a lot of stuff in front of it, but move this to the back a little bit. Okay, so now we're away. Okay, but it's still clicking a little bit. Why is that?
This is what's called background count, and it's different wherever you are. You know, different in Idaho, different in spots in Idaho. What it is this thing is picking up the radiation that the sun is throwing at us. The sun churns out all sorts of things. Churns out alpha, beta, and gamma, X-rays, ultraviolet light, infrared. They have magnetic storms that are called sunspots. Those throw out magnetic energy. And this is what the ozone layer is supposed to do. The ozone layer filters out this. Without it, we'd be cooked.
I see.
However,
literally.
Even though, literally you'd be cooked. However, what you're hearing, not on the table, okay, that's just what is coming down on you.
Okay.
You don't have to move. You don't have to worry about it. You know, everybody gets this.
All right.
People that live in higher altitudes have to worry about it a bit more because there's less atmosphere between them and space.
That makes sense. So,
Colorado.
Yeah, Colorado.
The top of Mount Everest.
Yeah. So the people that have that large telescope on top of Hawaii that provides all that clarity, there's a downside to that.
Yeah.
Okay.
Airplane pilots that fly, trans-ocean flights that are up 35,000 feet have to keep a check on how much radiation they've absorbed. It's a really kind of, how can I put it? Comes with the job, All right.
Sort of like this.
Yeah. All right.
Okay.
Now,
let's see.
All right. First thing, we're going to take the piece of wood, put the wood on the Geiger counter.
Okay.
Oh, no, wait a minute. Back up. Take this first. Sorry, Myra. And bring that on the Geiger counter.
In the container?
No, out of the container.
Out of the container. Yep. Wonderful. Okay, it has a little radioactive symbol on it, which makes me feel real good.
All
Okay.
right, so just bring it down. Okay, take that away. Now you can see that that thing was really screaming. All
Yeah.
right?
I got to tell you, on this gauge here,
Yes?
it's at 0 now, and now it's about 3/4 of the way
Yeah, it's
up the
about
scale.
it's about 7, I don't know, 700, 7,000.
Okay.
Now, take
And
the
this is AM241, so
Yep.
that's americium.
241.
So this would be the material in a smoke detector,
Right, right.
which we should all have in our house, at least one of them.
Yep.
Okay.
We'll discuss that. No, now
Yep.
take that.
Okay.
You've already put it there. Put
Okay.
the piece of wood over it.
Okay. Piece of wood.
All right. Now put that right down on the wood. Just leave it. Now,
Okay.
that's
so
that's hardly doing anything. Okay.
Yeah.
And it doesn't matter if it's a 1/2 inch or if it's perhaps 3/16.
Okay.
What you're listening to here is just the gamma rays that the americium gives off, okay,
Okay.
that go straight through the wood.
Okay.
But it's primarily an alpha emitter, so what you've done is you've just closed out all the alpha.
So I'm blocking the alpha,
And the gamma
and
rays,
the gamma
are
rays
still
are going through.
So now switch
Okay.
that for the piece of aluminum.
Okay. So there's the wood down. I'm just curious to see what a flimsy little piece of.
Alpha particles don't need a lot to.
No, they don't. This is flimsy. Okay, now what?
Piece of aluminum. Just stick
Okay.
it on there.
So here's a piece of 1/8"
Yeah, 1/8
aluminum.
inch aluminum.
Okay.
Okay, so just about the same.
About the same as the wood.
All right, so now we'll swap the aluminum for the lead.
Okay. Aluminum,
There's the lead.
lead flashing, like as he said, use on your chimneys.
Yep.
So again,
Not a whole lot of change.
so again, with both these materials, the wood, the aluminum, the lead, the alpha particles are being blocked,
And the gamma rays go.
but the
yeah.
gamma rays are going through.
Okay, so
Okay.
put the wood. All right, grab
Okay.
the strontium 90.
Strontium 90.
That's here.
Okay.
And the piece of wood again. Well, first put it in front of the Geiger counter.
Okay, so this is strontium 90, which is that one of the on the decay chain for uranium? Is strontium 90?
I don't. I'm not. I'm going to
We're
say
gonna
I
get,
don't know. Rather,
we're going to get to decay chains.
No. So that's pretty active.
That's-
right there. All right. So put the piece of wood on there.
Okay. You like the terms active? Doesn't alarm you.
Yeah. No. Active.
Okay,
It's,
active.
hot.
Okay, now again, the wood seems to block the alpha particles.
Yeah,
Okay,
yeah. But it's not blocking the other, and we'll show which one that is.
Okay.
When you put the aluminum on there.
Okay, so now I'm removing the wood, and this is strontium
Strontium 90.
90. Now I'm back to the 1/8 inch aluminum on the Geiger counter. Again, the alpha particles are being blocked.
Yep.
Okay.
And most of the beta. Now try the lead.
Oh, so this is a alpha, beta, and gamma emitter?
No. That's just a beta emitter.
Oh, just a beta
Just a
emitter.
beta emitter. But there are different
Okay.
levels of energy
Okay.
for any particle. So take the piece of lead.
Okay, here's lead.
So now all that's coming through is some gamma rays.
Okay, it's definitely slowed.
Yeah.
Okay, so that's gamma.
All right, so we're going to
Okay.
do the last one now.
Okay. Okay, so we did americium 241. This is strontium 90. These are all legal to have.
I bought those from Oak Ridge, place down there that this is their business. They make, these are calibrated amounts of the various isotope or element for people to use to calibrate their Geiger counters, scintillators, special machinery and all that.
Probably medical machine?
Yeah, medical machinery, but they're not, you can't build a bomb with one.
Mm-hmm.
You know, I could buy 100 of the cesium. All I have is 100 cesium buttons. I can't do anything with it. So, you know, it's, all right, so start with.
So Oak Ridge National Labs, that's one of our national laboratories, which is in Oak Ridge, Tennessee.
Yep.
Okay.
Yep.
And,
all right, so use the, okay.
Okay, so this is
Cesium.
Cesium-137.
137, which is a man-made element. Now listen to that.
So, a man-made element. Okay. Man-made. This is pretty active.
Yep.
Pretty active.
All right, try the wood.
Okay.
Wood first.
Yeah, definitely. Well, it's still pretty active.
Yep.
But not as active. Definitely. Now the aluminum.
That's pretty good for going through aluminum. That's,
okay.
Those cosmic.
Is this a, what type of emitter is this?
Gamma.
This is gamma. Only gamma?
Yeah.
Only gamma. Okay.
So we do the lead.
And then do the lead.
And it acts like the lead really isn't there. And gamma emitters will go right through lead. You need probably 4 or 5 inches of lead to stop the gamma rays.
Just for an experiment, hand me that piece of lead there. This is a few more layers of lead. Well, 4 layers of lead. Just hold that there. Strontium. That's slowed it down, but it's still. Okay. Okay. So, man-made. So, that element did not exist before man.
Correct. That
was not a trick question.
That was made in the laboratory.
Made in the laboratory. Yeah. And this is a result of nuclear waste. Is that true?
Well, it's probably a result of nuclear waste, but I have a feeling that it was made before the waste came into being. Otherwise, they wouldn't know what it was.
Right. Okay. All right.
No, a lot of these things, if you look on the periodic chart, we're not going to get deep into it, that you can see the man-made elements. And
this is the periodic chart. Okay.
Yeah,
you got that? Good.
All right, I just want to see something here. Okay, I'm just trying a little side experiment. This is a tube that was used in radar applications, the government. And it doesn't look like a tube, but it was. And I am just putting this, that's pretty hot. It carries radium in it. And as you can see, it's taken away most of the alpha, which is what you would expect.
Okay. So, the particles, we mentioned Niels Bohr, and he understood the atom and postulated that model of the atom. But in my reading, years before that, Ernest Rutherford worked out the understanding of these three particles, alpha, beta, gamma.
Through the years, there have been all sorts of contributions made by a lot of people into the understanding of radioactivity. And I could just imagine what it must have been like to develop some of this stuff and find out, because you're dealing with something you can't see, you can't feel, you can't hear, and yet it can cause damaging results in your body. And where do you go from there? You know, how do you let me put it this way. Theoretical physicists, in my book, are probably some of the smartest people on the face of the earth. Because typically when, say, you or I have a problem, we go, all right, I have this problem, how am I going to deal with it, and so on. These theoretical physicists are saying, I think there's something out there. I'm not sure what it is. I'm pretty sure. And they spend years, like the Higgs boson, they spend years waiting to see this thing, and then it finally comes to being.
Yeah.
You know, that is awesome as far as I'm concerned. That's
And they see it through, in sort of an indirect fashion, through experimentation.
Yeah, yeah.
Right. Like a little blip on a screen from a cyclotron. There it is.
They're dancing in the streets, you know.
Okay. Okay, so we have a lot of items here, but in our first show, we're not going to get to these items.
Right.
Okay. The goal of our first show was to provide a framework of the atom,
Right.
of radioactivity,
Yeah.
which I think you did magnificently in terms of describing the three particles. And some good demos.
Yeah. And that's all there are three particles. There's nothing else. It just...
Okay.
Yeah.
Well, what about things like the neutrino and the photon?
That gets into it when you get certain types of collisions and certain speeds of things. Like neutrons can move at certain speeds, okay? And sometimes you want them to go fast, and sometimes you don't want them to go fast. But it's there is so much to radioactivity that we could do a show every day for about 2 months.
Okay, and
we ain't doing
and
that.
we're not going to be doing that. However, there is going to be another show, Fun with Science, which we're going to get into more uses of radioactivity and where radioactivity appears in things that we use in everyday life, as well as things that were used during the past.
Right, and also an explanation about how a Geiger counter works.
Okay.
Which you didn't need to know that for what our demo was, but now, you know, next show I will explain what it is, and you can, you know, have a layman's.
And I'll bet this was made by someone by the name of Mr. Geiger.
Geiger Mueller is the...
Well, wrong again.
No, that's what they named the tube after.
Geiger
Mueller.
Mueller. So his first name was Geiger?
No, it was two people.
Oh, Geiger and Mueller.
Yeah.
Okay. Oh, okay.
So...
All right. Well, we'll pick this up at the next Fun with Science. We hope that this has whetted your appetite. Tom, thank you very much for being here with us,
anytime.
and we'll see you the next time. Thank you.